Okay, let's get started. So this is just a continuation of the previous stream where we talked about IL, which is a domain-specific language built specifically for the Cranelift, uh, compiler backend code generator, you can say. And I talked about, we basically went through an overview where we talked about what IL is and, you know, what you can, what was it designed for. And we went through some of the examples of how you can, like, what does I look like? We talked about that. There is you know a good README page for it. That's on the just include this one side here. So you could actually look at the Cranelift project, and there's a very good README page in there talking about IL. It says, what are the basic components in there, etc. Today, I want to keep this one going to be pretty short. I hope so. The reason is we're effectively going to focus on one thing, which is as a continuation from the previous one. A lot of the times when you start and dealing with a project that is it's relatively small when you compare it with LLVM, but as big as Cranelift, you might want to get to grips with how the project is laid out. What was what's the, where is what, basically, and why is it in that place? So it helps if you sort of think about those things. And today I'm sort of going to focus specifically on working with IL, because when we start working with IL, you'll see that you can pretty much get into like you know, a bit of a rabbit hole trying to figure out where things are defined, and when you're trying to debug stuff, what should be you be looking for, etc. So given that context, we'll dive a little deeper into how is IL used in the Cranelift project. And yeah, you might see me right now because I just got a standing desk, so I can now stand and do these streams rather than sit. That's a good thing. Um, so let me get started. So I've pretty much just to recap. So IL is this thing called instruct. It's a domain-specific language that is used by Cranelift to do basically things like instruction selection, or lowering of expressions. We've gone through all of this. There's not a lot of um, complexity in this. It's basically you have Cranelift IR and you want to convert that to some sort of machine instructions. You could obviously write this in Rust by hand and do that, but we discussed, this can get really tedious, and you can introduce subtle bugs, etc., when you're dealing with, let's say, a really large match expression where you're matching a whole bunch of cases and trying to figure out what needs to be done. So effectively, to reduce things like making less tedious and less error prone, not introducing subtle bugs, all that stuff, a domain like a specific language really makes things simple. But of course, the flip side for that, it's all trade-offs. You have to learn a new language, right? Um, Style is not very different, because if you've been working with Rust, it was built for a Rust-specific project. So there's going to be a lot of Rusty stuff in it. It has things like types in there. It is a statically typed language, and a bunch of things that we discussed in the last time. But effectively, long story short, you have your Cranelift IR, you want to convert, or you want to translate them into machine instructions, you're going to need IL. That's what we sort of went through over the last time. Now, in this stream, what I want to talk about is how do we read Cranelift's rules, all this IL stuff that we're talking about? How do we read this stuff? Because the README does a good job of introducing you to the subject. We went through this the last time, basic concepts of, how do you declare a type? How do you declare loosely put a function? And then what sort of data types do you have? You basically have things like your primitive types that can be mapped to a Cranelift type, or you can have enums, which sort of map to Rust enums. And then we've talked about functions and applying rules, basically a very functional way of writing things down. We looked at the basic syntax. Now, what I want to see is you take the same concepts after you have looked at that, and we actually understand how this is being used in Cranelift. So, what I have here is I've taken out the snippets just so that we can compress everything and make it very simple. So previously, when I talked about, say, something like this, I said, if you read the README page, you'll be able to see that in IL, if I wanted to call an I32, a Rust I32 type, an IL I32, I want to like refer to it somehow, I can just say that a primitive I32 in Rust is an I32 in Cranelift IR. And the same thing holds here. I want to talk about a high-level instruction, and I basically want to express this as an enum in Cranelift. This will effectively be translated into a Rust type, which is an enum. And then the other piece that you saw is you want to declare rules that attach to that make use of these types. So you can have a function that says it's called lower. I'm declaring it. It takes a high-level instruction and returns a low-level instruction, which is you see that over here. You see the high-level instruction and you see the low-level instruction. And you see that, they're basically enums. So you're taking one enum and producing another enum, and you're trying to express that in Cranelift. Sorry, using IL. So we went through all of this. I'm not going to again do a full recap of that. But effectively, what happens, you write all of this stuff, and then you get this little function. You get this function called construct lower, which basically does, instead of you having to handwrite this, if you write it in IL, that the IL code can be given to something called the IL compiler, ILEC, and it will produce this particular Rust code. So effectively, it's a code generator for Rust. But what we can do over here is we express our ideas in IL, and they get translated into Rust without you having to actually write this, this massive piece of code that can make things worse for, the programmer here. With that context, just to recap the previous pieces, you can see that the way to actually define a lowering expression, a lowering rule, is you can give it any name. You can just call it lower in this case. And I'm saying I have a Cranelift IR instruction. I want to lower that to some sort of a lower level instruction in this case. What we want to do is machine instruction. Now, with that context, you could obviously go ahead and look at the previous stream and talk about, at least the basics. With IL, if I want to actually jump into the project and talk about a very specific example, for example, there is a declaration over here. This is basically a function declaration. It has an additional keyword called partial. It basically means that the function does not always produce. Wait, there's a language reference for this. You can go ahead and look at that. Let me find that. Yeah, it's right here. So yeah, partial expressions. So IL's partial keyword on a term indicates that the term's constructors may fail to match. So basically, the entire function that's generated for each piece of IL code that you've written, it'll generate a lowering expression in Rust. And a lowering expression is just basically a gigantic match statement. So if your match fails, we want to figure out, we want to say that, we want to express that in IL in some way to say that it could fail. So if it does fail, what do you need to do? So because you could have things that are infallible, as mentioned over here. The IL compiler assumes that the terms constructors are infallible by default, that is. If you clearly specify it's partial, then the compiler knows that, the IL compiler knows that, this particular function may fail to match. So there must be a default case that we could probably end up with or something like that. Anyway, that's what partial means over here. So I can declare a function which could possibly fail to match, but it takes something called an inst and returns an inst output. An inst over here, um, well, I'll have to dive into other pieces, but assume that an inst is a Cranelift instruction. Technically it is, but actually it's an entity reference. So that's not the point. It's a Cranelift instruction which produces, if you give it some Cranelift instruction, it's going to produce the instruction's output. Okay. If the instruction were to be executed, what is the result that is produced? That's usually stored in a register and that's returned to you. That's what this function is supposed to be doing. And the way you write the body of the function is you start applying these rules. This is the whole part where I mentioned it's very functional programming like, right? So I've selected this very specific case for this particular scenario where I'm saying I would like you to match on the Iadd instruction. So before we go forward, let's basically take a look at all the possible instructions in Cranelift. Uh, Cranelift IR has a set of instructions that you can go ahead with, like that makes sense for you. So there's multiple ways of looking at this. I could simply go into the IR and look at the instructions section. Where is that? Yeah, yeah. And then you should be able to see pretty much all the instructions over here. But even better, I could just go ahead and show you all the instructions so that it's a little more clearer. By the way, this stream is just because when you're going through such a large project, it makes sense to uh, for your future self. If you want to come back to things and say, okay, what did I what what did I read and what kind of sense did it make to me? You can come back here and recheck your understanding. So what do I want to do? Yeah, opcodes. So all these opcodes are not effectively part of the implementation, but they're generated as part of a macro. You can see that all of these opcodes, which are things like jump, branch if, branch table, all the stuff that you see, all these are actually Cranelift instructions. These are obviously a higher level abstraction. They don't directly map to machines, but that's what we'd use to generate the respective machine instructions for the respective microarchitectures that you're targeting, right? And in this case, one important piece that I want to focus on is where is that? There's an instruction called Iadd in the Cranelift IR, which basically does what? It is it's an operation that takes two operands, X and Y, and produces, a resultant operand. Basically, it's the add instruction. And the reason I chose this is because it's very simple to explain this in IO, but it does cover pretty much everything that you will see when you're implementing or when you are writing your IL rules. So that's the Cranelift instruction that we want to lower to a machine instruction. I'll also talk about which particular machine instruction I'm talking about. So let me just go back. Yeah. So what's happening here is you've declared the function, and then you're saying this -1 stuff that you see, I'll show you that, is basically the priority of rule application. That means once you've defined your function, you start applying rules, as we discussed in the last stream as well. Here I'm saying this rule says that if you come across a match expression where lower is given this particular kind of an instruction, this whole thing will reduce or will basically, be reduced to an instruction, a Cranelift IR instruction. Then, if it's this particular pattern, then go ahead and replace that pattern with this expression. That's pretty much how you write IL code. And that will generate the corresponding Rust code that you'll be working with. But the reason I wanted to spend some time over here is because if you look at this very carefully, you'll see that there's a lot of stuff in here, and then you'll have to jump into many places. That's kind of what I wanted to simplify. The first thing that you see is lower. We already know that it's defined over here. It takes an instruction, returns an instruction output. But then you have this thing called hash type. which obviously does look like a function of some sort. It's not actually a function because this is what you would call a constructor, but this is not. This is called an extractor because it extracts something. I'll talk about what that is. I think we discussed this the last stream as well, but not in a lot of detail. And then fits in 32 again is the same thing. So everything on the left-hand side. So this whole thing is what I called the LHS. If you put something in there apart from the original constructor, all of that stuff is pretty much an extractor. Okay. Anything on the right-hand side, which is called the expression. So this is the pattern to be matched. And this is the expression that it's replaced with. If you see this, replace it with this. Pretty much. If you see this Cranelift instruction, you replace it with this machine instruction. That's sort of what we're trying to do. So the way this works is we need to break down what is has type, what is fits in 32, and what is type int, and what is Iadd. It's a good way to think about it from the reverse. I'll start from here because that's the first piece that we need to evaluate. Iadd is what? As I already said, Iadd is capital I add is a, we saw that here. Capital I add is a Cranelift IR instruction. And this is an extractor. It's actually a function that does something. Where is it defined? It's actually defined in, yeah, where is it defined? Yeah, it's defined right there. Just let me just go back to my visuals. Oh, sorry. So if I go back here and I just look at the CodeGen repo, the Cranelift CodeGen part of the repo, and I go into any one of, I'm not going to go into the RISC-V 32-bit because I'm working on that. Let me go to RISC-V 64, which is pretty much the equivalent of RISC-V 32, except for 32. Yeah, except for the fact that this is 64-bit and that is 32-bit. So what will I say? If I see this, I want to figure out where this extractor is actually defined. So I've already mentioned that here. It's actually defined in something called lower.il. So if I go click here, you'll see that. So you'll see that the first rule for Iadd, first things first, we see that the lower constructor is defined over here in IL. And then I am looking for Iadd. So rules for Iadd over here. This is the base case, which you can have various kinds of add operations, but this is like the bare minimum. You have two operands, you want to add them, they're integers. That's what you want to do. So this is where it's defined. And now when you try to look up Iadd, you'll be like, you won't find it. That's exactly the point of the stream. You won't find it in lower itself, but it's defined. So there are things defined. IL rules are defined in multiple different places. They can be IL helpers. They can be things like extractors or internal extractors or external extractors, but they're all defined in multiple places. There's a reason for that. I mean, when you go through the repo, you'll get it. But when you want to find Iadd, you won't be able to find it. So where does Iadd actually exist? This is the definition for it. And it exists in the build artifacts. That means when you actually do a build of Cranelift, at least the Cranelift CodeGen part, it's going to produce an output folder in the target directory. And in that, you will find a lot of build artifacts, which are made use of. Like if you've written a macro, at build time, your Rust code is generated. Similarly, over here, although the build process is a little more complicated, so you actually have a target directory with a bunch of artifacts in there. You can go look at them in there. So that would mean if I was to just go and look at the target directory, look at debug and build, I should be able to find, there's another way to do this. You don't have to do exactly what I'm doing. The project actually talks about, you enabling some features to actually have the build artifacts present in your repo itself. But again, that'll mess things up. So I'm not doing that. So if I go click on out, you'll find cliff_lower IL.
And if I search for Iadd here, this is where we find the definition. And as you can see, it's we've declared it. Iadd takes in two values and returns an instruction, but it's an extractor. The difference between a constructor and an extractor, a constructor behaves exactly like a function, right? But an extractor actually does the reverse. It takes an instruction and tries to, produce the arguments. That means when you look at the equivalent Rust code that is generated in place of an extractor, its job is to actually take, when you look at it in IL, it looks like, it's taking two values and producing an instruction. But the actual Rust code, you will see that it takes in the instruction and produces the two values. That's the extraction that it's doing. In this case, Iadd is basically what you would call an internal extractor. So these two parts. One is the fact that extractors work on actually taking results and produce the arguments. That's one. The second thing that they do is when you don't see the extern keyword, which I will show you as an example as well. If you don't see the extern keyword over here, it means that this is an internal extractor. And internal extractors are just basically they don't get converted into Rust code. They simply map to an actual external extractor. In this case, was that Iadd, when invoked like this, Iadd when invoked like this will actually map to inst data. Inst data is actually an external extractor. Now, the moment you go back and you try to find where that is, you'll be like, okay, that's not somewhere else. So it's laid out according to what you'd intuitively think, okay, this file should be in this, folder, or this should be in this directory or whatever. It's laid out in that manner. It's not laid out all in one place. You can just find everything in one place. That's not how it's laid out. That's another piece. So if I see prelude underscore lower dot I here, so let me go back again. So yeah, this is exactly what I ended up doing, which is jumping back and forth. So I thought I'll just make this simple for myself and also reiterate this to myself and make a video so that when I come back in the future, I'd be able to clearly tell what was going on. Anyway, so instruction data, if I was to look at, where was that? Prelude lower. If I go look at that part, I'll be able to see that. So I just, go ahead and do that. You'll be able to see that it's declared over here. So this is an extern extractor. And as you can see, we saw that at least when we saw the lower, declare partial lower, and then takes an instruction, returns an instruction output. You saw that we basically tagged it as partial. Now you can see that this particular extractor is infallible. That means you call it, it's not going to fail. It's always going to produce a result. And if we wanted to see what does this produce, I've also got that just so that, we don't lose track of things. So if I went ahead and looked at instruction underscore data as implementation, you'll see that it actually takes an instruction and returns a instruction data. That's effectively what's happening here, because if you see instruction data, it's in Iadd simply maps to this. And over here, you can say that it's supposed to take an instruction and it's supposed to produce these two. This whole thing is what you'd call the operands. Okay. It's supposed to produce this stuff. That's pretty much what the instruction data is going to do for us. It's going to take in an instruction. Where is that? Sorry, just a minute. It's I need to, if you scroll down, you'll be able to see that this instruction data is defined in something called ILRS, because this is not generated automatically. This is an external constructor, which means we provide the logic. So any external constructor or extractor is where we insert arbitrary logic that's not code generated. That's kind of what you'd see here. So if you were to go back to something like
Where is this again? This is in machine instruction aisle. So if I go look at machine instruction aisle, I should be able to find it here, right? So, well, I mean, when you read it, you'll be able to figure out exactly what it's doing. Uh, so I'm not actually talking about that right now, but basically you have an abstraction called the function type, and it holds the data flow graph. You get the data flow graph, and in the data flow graph, you're looking up a particular field that says, okay, what are all the instructions that I have in this function? Give me the instruction by this index. The moment you say that, you're going to get that instruction back. That's what instruction data is. So instruction data is going to return the data associated with that instruction. What is the data associated with that instruction? It's basically the opcode and the operands. That's pretty much. And then you also get some additional data if you want, depending on whether or not that instruction has additional data. All right. So that's in a nutshell how you would, you're starting to go, you're starting to piece by piece unwrap exactly how you'd read an IL rule. So the first thing I said is this is what you need to look at. And when you start looking at that, you'll start going down this route. You'll see that effectively it turns into an external extractor. All right. And the way this thing is implemented, the way the Iadd actually gets converted into Iadd, Rust code, rather than show you the actual implementation in the generated code, because that's pretty huge. I'll just show you what the constructor looks like. So you generate the lower constructor. It takes an instruction and produces an instruction output. By the way, this is partial, so it's going to be an option. It may or may not, they may or may not be a match. So you might get a match, which is something. You might not get a match, which is none. Right? That's why it's an option. What happens is you take the argument and then you say, give me the instruction data for that. Right? That's the first thing that you do. That will tell us that, okay, so assume that we're dealing with the Iadd instruction in Cranelift IR. It's going to say that, okay, that means, as you probably saw um, in, okay, just give me a minute. Maybe a little lower. So let me just pull that up in my file, sorry, VS Code, so that it's simpler. Right. And if I was searching for Iadd over here, you'd see that the first thing that you see is instruction data should basically produce, it should take an instruction and should basically produce this, the opcode plus, whatever the operands are. And that's sort of what you see here when you look at the Rust code. The instruction data will take in the argument, which is instruction, and then it produces basically the matching arm that you were looking for. It says, okay, so if I'm looking at an Iadd instruction in Cranelift IR, that means uh, the match, it should have matched to this particular variant, which is called this particular variant of instruction data called instruction data binary, as you can see here. Okay. And within that, if I'm looking for the opcode, which is Iadd, because you can have many binary instructions, you can have a subtract, an add, multiply, whatever. I'm looking for an Iadd. So that's the second part. And with that, and with the what you'd call with the operands to that Iadd operation, which is right here, it's actually, this is capturing it in an array, but doesn't really matter. It's the same thing. You get X and Y. You can go ahead and start using that to build your uh, rather long Rust implementation of your lowering logic. So if you had to write all of this, you can imagine if I just showed you what it looks like. I mean, if you were to just look at let's say in the generated constructor, if I wanted to look at something like, uh, uh, so this is the main constructor, the lowering constructor, which basically takes in any Cranelift IR instruction and then produces the appropriate machine instruction, as is the instruction output. Um, if you were to think about it like that, if I basically wanted to show you where does this end, you'll see that this thing ends at, it's roughly about 10,000 lines of code. So if I was to say 21,869 minus whatever, 1104. Yeah, approximately, about approximately 11K, little less than 11K. That's 11,000 lines of matching stuff that you'd have to do, right? That's a lot of stuff to write and write correctly. This can be really long. Just this one single, function, right? So that's exactly why IL makes things a lot more easier if you were to dive into it. But yeah, I didn't want to like capture all those 10,000 lines of code and show you where it is. You could probably look at this and then go look at the generated code for yourselves if you have more questions. So what's happening again over here is now that we are at Iadd, the very first arm, which is, well, I want to see this. Yeah, the very first arm, which is this part, we've now pretty much figured out that, okay, we basically want to apply this rule to match on this particular pattern, which is of a binary instruction type, which has got these operands, and it's basically an Iadd opcode with these operands. So that's the first thing that we've done. Second thing that we need to do is we need to figure out what is this tie int and fits in 32, etc. For that, if you just scroll down a bit, I've also got what that value array was. That's like you previously saw X and Y in the Iadd operation. We store them, at least IL stores them as an array of 2 elements. Anyway, that's fine. You'll see that. Let's break this down by looking at tyint first. And if I was to see that, where did I capture that? Did I not capture it? Oh, yes, sir. Right. So if you went ahead and looked up tyint, where is that? Tyint, if you went ahead and actually looked it up, again in the lowering expressions section, sorry, in the IL code, you'll see that it's, as I told you, everything on the left-hand side is an extractor. So ty underscore int, which is the type of the integer, is also an extractor. But the interesting thing is both of them are not internal extractors, which means they don't map to some external extractor. They're an actual external extractor. So they have a direct definition in Rust code that you write. So if you actually went ahead and took a look at that, you would be able to see that it maps to this particular Rust code, which is it's basically going to take the type you provide and it's going to figure out whether or not this is the type integer. If not, it's going to say, okay, it's some type or, return whatever the other none cases. So that's the job of type it. So in our case, what you're trying to say is, let me go back here. The type that we've been provided with, we want to figure out, we want to be clear that this is indeed of type integer, right? This add operation that we're doing is on 2 integers. If that is the case, then figure out whether those integers actually fit in 32 bits. This is another section saying, okay, what is the width of the integer add operation or the operands to the integer add operation? In this case, we want to ensure that they are actually of type, they fit in the, 32, sorry, they fit in 32 bits. And in order to figure out where that's sort of explained, you can, again, scroll down and you'd find that again in the prelude over here. you'd see that, okay, let me just check the types bits if it's less than 32. All of this is implementation by the programmer, in this case, whoever's contributing to Cranelift, in this case. And then if it's less than or equal to 32, that's fine. If it's not, we just say that, no, it's not. So that's what this part gets right. And these two are arguments that are actually passed to as type. As type is it's a little more involved because has type is used pretty much throughout the repo. You'd see it's used everywhere. Its definition is it takes a type and an instruction, and then it's supposed to return an instruction, except that it's an extractor, so you'll flip it around. You say, given an instruction, I'd like to tell you what the type is, that is the result, the type of the result that's produced by that instruction, and I'll also return the instruction itself. Okay, that's kind of what's being said here. So I want to do both of them. But then when you look at its definition, you see that has type is basically an external extractor, and it maps to two things. And is a keyword in the language. You basically, it maps to result type. And when you look at result type, it in turn maps to, it's an internal extractor that in turn maps to, these two things. So here is where you will see that both of them are actually defined, right? First result, that means an instruction can obviously produce multiple results. You can have, for example, if you do a divide operation, you might get the quotient and you might get the remainder. So there's two different results that you might have received from a single operation. So in this case, we just want to pick the first one. That's why we're saying first result, extract the first result value for the given instruction, and then extract the type of that value as well. So we get both of them through these two extractors. And these two extractors, which is first result and value type, are defined again in your machine-specific IL implementation. We basically look at the data flow graph for this, and we figure out, okay, where of the results that I have for this instruction, which one you want the first one, and then what's the type of that. So all the same stuff, not a lot of change over there. And if you were to look at how this maps into Rust code, you'd see that over here. You'd see that the moment we've constrained ourselves to the Iadd operation, we first go check what's the first result. Once we get the first result, then we check what is the type of that value that we've received, and then whether or not it fits in 32 bits. So there's some other rules that can probably get in here. That's not important because, as you saw, the Iadd operation can have multiple rules. For example, it's not here. Yeah, let me go back. So if I just no this man, I'll look at RISC-V64 because that's more interesting. If you look at this, you'll see that this is the base case. And then you have multiple add operation kind of rules that can be applied. It can be stuff for things like I64, it can be floats, it can be a whole bunch of different kinds of add operations that you'd probably want to do, right? There's a lot of stuff here. So all of that stuff can probably fit in there, but this is the base case. If none of them match, then you're probably going to match the base case, right? That's why it's at the end, the, of the super match block. Anyway, so that fits in 32. And then we also do the same thing again. We check to see the type of that. Once we're good with all of this stuff, then we get into the space where we say, we want to go ahead and now that we've particularly, when we go back to, when we go back to our definition again, so far we're only looking at this rule, nothing else. We're just looking at one single rule, right? And when we're looking at that rule, now we've basically pretty much, we've looked at a pattern, but we've looked at all the constraints on that pattern. I want to look at this in this pattern, within that pattern. I want this particular pattern, within that pattern. I want this pattern. That's how you've narrowed it down to exactly what you want to match on. And once the matching is done, you basically want to replace that with this, right? That's exactly what you want to do. It's kind of what's going to happen next. If you see here, once once you've done the matching and you clearly exactly at the point that you want to, I want to replace that instruction that you just saw with this, which is, where is that? This particular instruction. So a better way of looking at that would be here. Okay. So I've just described all of this. So everything on the left-hand side is stuff to be matched, the pattern. They're all extractors. We've looked at that. Now we're coming into the right-hand side where these things on the right-hand side usually are constructors. Not usually, they're constructors. You create stuff with them. So if you try to expand RV underscore add W, you can already see it's very close to the RISC-V add instruction, machine instruction, but not very close because you've got this prefix over here. Now you go look at the definition for RV add DW. Again, this thing is defined in one of the IL definitions. You go look at that over there, you'll be able to see that. And it's a better way for me to do this is for me to show you where it's defined. So I believe it's defined in the add instructions over here because it is an instruction. And right. So if you go look at the definition of it in the IL instruction, you'll see that it's over here. It's nothing but a constructor that simply says, okay, if you find this particular expression, simply replace that with this, right? That's pretty much what we want to do right now. And that's effectively what's going to happen here. So we're going to replace this expression with this expression. And when you want to go look at that definition over there, you will see that ALU underscore RRR, which means you take two operands in two registers, then you produce results. That's also in another register. So this is not like the Intel x86 kind of an add where you reuse one of the operands registers for the add. You have a third register. So it's a reduced instruction set in that way. Anyway, with that said, when you go look at this particular implementation, be like, okay, there's a lot of stuff going on up here. What's exactly going on? You'd see that this particular definition that you see is pretty much translated into this. So if you go and look at construct lower, you'll see that, okay, I'm going to go ahead and construct the RV underscore add. Let's look at that. The first thing that it does is it puts values into registers, right? That's the first thing that happens. And then it calls the constructor, which is ALURR, as you saw in the IL definition itself. And here is where the actual work happens. All of this stuff will end up here, where it's actually going to emit the actual machine instruction into a machine buffer, the bytes that will be later used to create your whatever, machine code or executable or whatever you call it. So the point is to get to this particular, place. So that we can clearly say, if I'm looking at a very specific instruction with all those constraints that I talked about, and I want to appropriately map that, or rather convert that to a machine instruction, we go through all of this and we end up here. So I'm not going to go into each of the functions because some of them are pretty much self-explanatory, but the important ones are RV underscore add W calls, ALU underscore RRR, and ALU RRR is the one that actually does the emission, which means it's basically going to take a machine instruction as an input, and it's going to produce the necessary bytes that will basically be like an add W or whatever that is when you read that buffer. So there's a type called the Mac buffer, which is the machine buffer, which we're not covering. I'm just talking about today. So we'll just limit it to that because there's many pieces that you might get confused with when we go down this route. Okay, So as you can see over here, the signature of the function should say it all. I've basically received an ALU operation with two operands for arg1 and arg2. So I fill them up. I say that put the register in the resultant, uh, the result of that operation to v4, and then let me build a machine instruction for me, pass it to Emmet. Emmet is going to do a bunch of things and generate the right code for it. And then whatever is the result that was produced because of putting this instruction together, basically the register that you get back is what is returned. That's effectively what happens in totality of when you want to lower an IL rule, something that is as simple as Iadd, an Iadd instruction uh, all the way to machine instruction. So you go through all of this. So this pretty much covers a, many different parts of IL. I mean, with this much information, I think you should be able to read IL easily. All right. There's other stuff you might find, other syntaxes like the @ symbol and the $sign. There's not too much of it. There's just what you'd say convenience things that are added to the syntax. But this is pretty much it. You've got things like constructors, extractors. Constructors and extractors can be internal and external both. Extractors, if they're internal, they simply map to an external constructor. And external constructors can be defined in one of many places that basically you write. It's just that the arguments, the difference between a constructor and an extractor is extractor extracts something from the result. Constructor takes in the arguments and produces a result as such. And then you can keep applying these rules and generate massive match cases and match statements and make it very simple for you to write, a lot of this stuff. So uh, another good way of looking at why you'd want to do this stuff in IL is if you went ahead and looked at something like the lowering thing for IL, if you just looked at the whole, uh, it's about 3,000 lines of code, all right? But if you actually looked at the implementation for this single function, as I said, is close to 11,000 lines, a little less than 11,000 lines of code. And then you have to meticulously write this match expression for each, sort of instruction with the different opcodes and the different use cases, etc. There's a lot of stuff that can go wrong, quite simply put, right? So that is what IL helps you avoid. IL also has other things that I'm not going to discuss, things like they're also looking at a way to talk about formally verifying the IL code that you write so that it's sound and stuff, mathematically proven and stuff. So you would add a little more to the syntax and say that, okay, I want this spec to be made. It's very much like a deductive verifier. If you know things like Rusty or Crusoe or anything like that, that's something that makes sense in those cases. But yeah, just to work with IL, I think this is sort of what you need. And I'm pretty sure it's going to be useful to at least people like me who don't know anything about compilers. And you just land up here and you're wondering, oh, yeah, I don't know what's going on. This might help. So, yeah. Um, in case if somebody is from the Cranelift project is watching this, if you think that I got something wrong, please do let me know because it took me like a day or two to put this stuff together. And I was really running through different files to figure out exactly what's going on. So I believe this is correct because it does check out from from what I've written versus what's being generated. So I think it works. Or I think it's right. Sorry. Okay, that's about what I want to cover. This has been all about how do we read Cranelift's lowering rules. Now, the same thing can be applied if you just want to define your types and stuff like that. Well, the same kind of syntax can be applied, but lowering, Cranelift IR to machine instructions is what this is particularly built for. So this is effectively what you need. All right. I think that's about it. I was hoping this was going to be small. I hope it's small, the size of the string that is. Anyway, thank you very much. Have a good day.